Hello everyone, welcome to a new little video I found. This is from the r/GoPskeptic subreddit that I check out very infrequently, but today there was a video there that I've looked at. It was only like 3 minutes long. It's 4 minutes. I'm sorry, 4 minutes long. That claims that light years should be impossible, or that's the title. At least you will see in a short bit what they actually mean with light years should be impossible. Oh, sorry. Oh wait, I'm not sure I can play the sound. Let's leave it off sound. Yes, the photons from the sun traveling at the speed of light reach us in about 8 minutes. So in these 8, the wording here is very weird. They say that in that 8 minutes, the perspective shrinking of the sun shrinks like 400 times smaller to the exact same size of the moon, which is not true. Sometimes the moon is a bit smaller, sometimes the moon is a bit bigger. They are only the same, like very few days in a year. But you could say that on average they are similar size. I'm fine with that. I wouldn't argue that, like, because they make it sound here that the perspective shrinking has something to do with time, which of course it has not. It's a mere fact of geometry, if you will. If something is further away, it gets smaller. It has nothing to do with time. But they use kind of over the bridge of the speed of light. You can technically make this statement, yes. So if something takes light 8 minutes to travel, if you will, this object then shrinks by about 400 times. This is essentially what they are getting at here, which is about true. By the way, very nice pictures here of both the sun and the moon. Yeah, so where they're going at here, I'm trying to fill in because I don't want to play the music. So what they're getting at here is that if you moved the sun further and further away, it will of course become smaller. Again, very weird wording. Essentially, they are saying that that's 16 minutes here is, wait, let me get back. No, I can't go back frames. I'm sorry. They say that 16 minutes, so twice the distance, is half the size that you would see at the distance that it's now, which takes light 8 minutes to go. You might as well say those are light minutes. And they go on like that, and once they reach, I love how the moon, by the way, can I just mention, my videos are pretty shit, right? I know that. Sorry for the swearing. My videos aren't exactly produced on a high time budget, nor on a real budget. I'm just throwing things together that I think are kind of okay. But I love how with almost every cut the moon also moves, which like, I mean, at least like clone the slide that you had before, but whatever. So essentially what they're saying at right now is that at 64 light minutes, the sun would be about this small to the observer in comparison to the moon. And now comes the hanger of it. Now comes the interesting point here. So like that's also a funny statement. Like, even if my math is wrong, which, I mean, well, if your math is wrong, your argument might change. So I mean, at least confirm. I didn't check the math. I just assumed it is correct. I'm trying to address the higher point, right? And now they're comparing it to Tau Ceti, which is the closest G-type star with similar temperature and luminosity properties and slightly smaller than the sun. By the way, if I just mention it here, I am almost completely certain that this is not a real observation but a simulation. Stars that are outside of us, like pretty much any object that are outside of our solar system, cannot be resolved. Like, oh, okay, that's wrong. Stars that are that far away cannot be resolved usually with objects that we have. Now you can partially resolve them with interferometers, although the resolution there is extremely poor. There is a radio was it radio? No, it can't have been radio. There was some observation of Betelgeuse in like 2018 or something, where they partially resolved it, which was really cool. But usually that's not the norm here. Yes, Tau Ceti is 12 light years away, and it is visible to the naked eye. And that's the thing. How would we see any star smaller than, with an E, our own 12 light years away, using blah 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 blah. So what they are saying here essentially is that this thing would have such a small, if you will, angular resolution that we wouldn't be able to see it, which is an interesting thought and at first makes sense, right? But that is not how vision works. I will explain that in a bit. I think they have finished their point here. I'm not 100% sure. Nice pictures again. Yes, we have seen these previously. Yes. And I'm afraid that this is where you're wrong. At least you say that I think it's impossible, and I think it is very possible, and I will quickly show you how that is. So let's have a look at how we actually see stuff, right? We see things with light, obviously. Light is, depending on how you see it, a wave or a particle, or kind of both actually. And we see it by the rods and cones that are at the back side of our eye. They're not only at the back side, but that's where we are going to be focusing on. And these things, these cones and rods, they can turn the energy that comes in as photons into, well, first of all, an electrical and then a chemical signal being transported directly to the brain via the optical nerves, right? So let's zoom in a bit and see how that works. It works the following way. This electron here is the electron of an atom, and if a photon comes in, it may hit the electron, shooting it out of its atom, and this electron then bumps into the nerve, and the nerve is then causing, depending on how we're looking, I'm not a biologist, either a electrical signal or through causing a chemical reaction, a chemical signal. Roughly, very roughly, once every 24th of a second, this electron kind of comes back. So if all the photons, more or less, this is a bit simplified. Again, I'm not a specialist in human vision by any means. All photons that hit within 1/24th of a second are seen kind of as the same picture. That's why movies that are above 24 seconds or at 24 seconds seem like continuous motion, more or less, right? So this is what happens. We see photons, right? We see photons, and they bump into electrons, and the electrons are then being recorded by our body in either directly through the nerves or via chemical reactions that are caused by the electrons. So more photons means brighter light, and we can see things resolved if we get photons from many different positions, and our eye just puts them together, right? Right now in front of me I have my phone, and my phone obviously has an angular resolution to me, and I can see that my phone is in fact not a point source but an extended object. However, if you move an object further away, it doesn't necessarily mean that you can't see it anymore. If it gives off enough photons, you can still see it, just not resolved. You then just see a point. And I have actually made myself the work of calculating if it's feasible to see a star that's that far away with our naked eye. And of course the answer is yes. Let me quickly walk you through my calculations. Let's say, and I'm being very pessimistic here, I'm putting our sun at 10 parsecs away. Now, I'm an astronomer, as you know. I'm currently writing my master's thesis in astronomy. I use parsecs. 10 parsecs, they put it at 12 light years because they're using Tau Ceti. I'm using our sun, and they arbitrarily more or less put it at 10 parsecs, which is about 32.6 light years. Okay, so first things first, we calculate the total radiation of our sun, which according to the Stefan Boltzmann law, which I'm not going to go through all of this, I will just briefly explain what I did, and you can look through more details if you're interested. Also, if you're interested about any of my calculations, feel free to contact me. So the power of the sun at the end turns out to be roughly 4.10 to the 26 watts. This is 4.4 times 10 to the 26 joules per second. This is the power that the sun puts out, if you will. Now let's have a look at the average energy of a photon from the sun. The peak of the radiation that comes from the sun is about at 500 nanometers. So the energy of a photon for a wavelength of 500 nanometers, it is about 4 times 10 to the negative 19 joules. Very, very little energy, because photons don't carry much energy, especially not at the visible range. The sun, you can just divide this, right? You take this value and you divide it by this value, and you reach the conclusion that the sun gives off about 10 to the 45 photons every second. Okay, cool. Now, let's place our sun at 10 parsecs. We have now 10 to the 45 photons are spread over the surface area, kind of, at our distance, right? All of these photons, supposing that they're being shot out equally, which is a very reasonable assumption to make. The surface area of the light sphere at the distance from us to this sun at 10 parsecs is 1.2 times 10 to the 36 square meters. That leaves about, I'm rounding here, about 10 to the 9 photons per square meter, which is about 1,000 photons every square millimeters. Now, the opening of your eyes at night is about the 6 millimeter range. It's somewhere in between 4 and 8, so I put just 6 down as a middle of the road value. So that means that roughly, when you calculate the surface area of your pupil with a 6 millimeter diameter, about 29,000 photons hit your eye from an object that is as bright as the sun at 10 parsecs away. Now, I had to look up how high the quantum efficiency of our eye is. The quantum efficiency just means if 100 photons hit your eye, how many of those do you actually can actually be registered by the kind of visibility sensor that are our eyes. And I found a paper, I will link it in the description, that talks about a rough 8% quantum efficiency, although they also note that sometimes it's about 60% depending on where we hit. I'm going for the most pessimistic case in here, just so you know that my calculation is fair. So from that, 8% of 29,000 is about 2,300. So 2,300 photons hit our eye every second from an object that is as bright as the sun at 10 parsecs away. You could now divide this by 24 to see if you know, but that still checks out. But still over 100 photons every 24th of a second. And I read up that an eye can reliably see, also in a paper that I will link in the description, can reliably see 10 photons in about 300 milliseconds. So our value is a lot higher than that. Rounding up to a second from this value, we need about 33 photons every second for us to see an object with the naked eye. We have way more than that. We have 2,300. So, to answer your question, yes, this star should definitely be visible, and mine is about 3 times further out than Tau Ceti, and it's just giving off as much radiation as the sun. It should be visible, but of course not resolved to the naked eye. If you use fancy interferometry and measuring techniques available to modern astronomy, you may be able to resolve it. Haven't checked, and it's not important really. So, with that, I will go back to the video because there are actually a couple of more claims that I would like to talk about. So with that, I think we can say that, well, not logical is just wrong. You haven't done any of the calculations. You're just saying that because you can't imagine it. it's impossible. That is very much personal incredulity on your part. Should you ever see this video, which I doubt that you would, because no one sees my videos, which is fine, then I would love to hear an explanation of where you think I'm wrong, or what you think I am doing wrong, or feel free to recalculate it. Maybe I made a mathematical error. I only spent like 15 minutes on that. But let's have a brief look at the rest of the video, and then we'll conclude this thing. Very nice photographs, but I believe those to be composite. I very much disagree, and so does the rest of science. As I've just shown you, that is very wrong. Especially with modern measurement techniques that have, like, our eyes are not good telescopes. If you have a telescopes with a quantum efficiency of 30% and like a opening diameter of multiple meters, you can see so much more. Also, with a modern photosensor, you can choose the integration time. You can that means that you can add up all of the photons that you can see over minutes, or like multiple seconds, minutes, hours, or even days, right? So we can see the faintest of objects with these techniques. That's not true. The stars change position all the time. Just look at Bernard star. This change is just so small that you can't really make it out with the human eye, but you can definitely make it out with telescopes. Also, I assume you didn't research that claim at all. That is correct. Well, almost the same as the sun. Obviously, almost the same as the moon. The moon has its own kind of velocity component to it that the sun doesn't have, because the moon is orbiting Earth and we are orbiting the sun. That is correct. I mean, it does a bit distort due to the atmosphere, but it doesn't shrink during sunrise and sunset. That is very correct, and it shouldn't, by the way, because we are orbiting around it, so we are at a roughly constant distance. It's not the exact same size. Again, sometimes moon is bigger, sometimes the sun is bigger. That's correct, although again, they move a bit differently. The moon is a tad bit faster usually than the stars. And not exactly the same. Close, I give you close, but not the same. Well, that is just plainly wrong. We can clearly see parallax measurements for multiple stars. How else do you think we came up with the distance to the close stars? I do apologize, something fell off my desk. How do you think else we came up with the parallax distances to the closer stars in the first place? Yes, we can see the star trials. They can very well be demonstrated with the heliocentric model, and it's in fact very easy. Just confirming my prior hunch that you did not have a look whatsoever. If the stars during a night, for practical purposes, do not move, and so they're kind of a constant picture, if you will, sometimes also called the celestial sphere that's around Earth, and Earth rotates, you would exactly expect what we can see here. You can also see that the Earth is both is spherical when you have a look at the South Pole, because they are rotating in the other direction, only allowing for the possibility of at least something that's roundish. Other measurements, such as the incremental drop of the Polaris, reveal that it has to be something close to a sphere. That's just wrong, and lazy, to be real with you. I mean, you could have just done 12 minutes of research and you would have found how it actually works on a globe. But then again, you're not out for doing proper research. What you're out for is making claims and trying to debunk things. But what you're really doing here is making a fool of yourself. I mean, they do, right? But we're also moving. So you have said, and so I have refuted. Again, I would be absolutely thrilled to know your reply to this. I will link this video in the description. It's not a video that's on YouTube, it's on Reddit, so, you know. But yeah, with that, I thank you very much for watching. If you did enjoy this video, please consider leaving a like. If you enjoyed it a lot, maybe consider subscribing. And I will see you in the next video. Good day!